Okay, so this tutorial will be continuing with C++ STL. We'll be starting with STL iterators. So from last tutorials, we covered C++ templates, and we started the standard template library with the vector class from the containers library. And today we're going to extend it to iterators. What is an iterator? What operations can I perform with an iterator? And we'll be comparing the iterators within the list and the vector container classes. So what is an iterator? An iterator, essentially within the STL containers library, it points to one element in a container. It's defined for all containers in the STL. And similar to a pointer, it points to one element in that container. It allows us to access an element in the container, also similar to a pointer where you can dereference the pointer and read or write into it. An iterator allows us to move between the elements in the container using a similar to pointer arithmetic operations. The iterator is restricted in the STL to only the efficient operations that could be done on each container. For example, if an operation is not efficient enough for a list, then that operation is just not defined for the list. And we'll be covering that later. So using iterator to access an element in a vector, or using the operator square bracket to access an element in a vector or array. The difference, operator square bracket implies random access. And by random access, it means that given an index in this container, you can access it by just adding that index to the address of the first element in that array. And you can access that in a one time. But random access is not supported by all data structures like linked list. For linked lists, you have to traverse it from either the head or the tail to the other. In STL, all containers have iterators defined, but they have different types. For the vector of int iterator is different from vector of float iterator and is different from list of integer iterator. These are three different types of iterators. For the function class, we have covered the operator square bracket to read and write the elements in the vector. We have covered the pushback function for insertion of new elements. We covered the size function to query the size of the vector currently. And all of the above can be done in one time. And today's new functions, we have, for iterators, we have the begin, which returns an iterator to the first element. The end function returns an iterator to the element that's one past the last element. And this is used for bounce checking. So visually, begin is at index 0. End is at 1 past and -1. So this element doesn't really exist in the vector. And let's consider these cases. So we have a vector of integer with numbers 1, 2, 3, 4. Case 1, we're defining a vector of iterator IT and assign numbers.begin into it. Is this operation allowed? Who thinks this is allowed? Show of hands. Who thinks this isn't allowed? Okay, this operation is allowed. It will point the iterator to the first element in the vector. Now, we have the IT iterator here. We assign 5 to IT. Case 2, is this allowed? Anyone thinks this is allowed? Anyone think this isn't allowed? You're right. This is not allowed because 5 is an integer, IT is an iterator, and an iterator is basically an object that's created from a class. So this is not allowed. Case 3, IT++. Who thinks this is allowed? Who thinks this is not allowed? Yeah, you're right. This is allowed. This will point the pointer to the next element. IT minus minus. Who thinks this is allowed? Who thinks this is not allowed? This also is allowed. This will point the iterator to the prior element. Now, case 5, integer x equals to dereferencing of IP. Who thinks this is allowed? Who thinks this is not allowed? This is still allowed. Dereferencing of a pointer will just go to where that element is and we can read it. Now, this is a condition. We're checking IT not equal to numbers.end. Who thinks this is allowed? Who thinks this is not allowed? This is still allowed. This will check if the pointer is pointing to any element in the vector, not at the end. Now, IT less than numbers.end. Who thinks this is allowed? Who thinks this is not allowed? This is still allowed. So up to here, it's very similar to pointers. Like you can do plus plus minus minus dereference and less than. Now case 8. Dereference IT equals to 27. Who thinks this is allowed? Who thinks this is not allowed? Yeah, this is allowed. You're able to write into wherever the iterator points to. Now, last case, IT equals to numbers.begin plus 2. Who thinks this is allowed? Who thinks this is not allowed? This is allowed for vectors. This will point to the third element. Numbers.begin points to the first element plus 2, then moves it backwards by 2. Looping through a vector by iterator is then very similar. So the first example uses the indices, which is what you're used to do. We start from index 0 and we move up in the vector using the index. Using iterators, we first declare the iterator type, which is std vector of int iterator. Initialize to the first element. Ensure that the iterator does not go out of bounds. So it's not equal to numbers.end. And advance every time. Element is accessed by dereferencing the iterator. Is this clear? And let's move on to the first exercise. For the first exercise, we're given a vector of integers, and we want to, using iterators, loop over the integers vector, and we have this empty vector of negatives. We want to insert all of the negative elements into the negatives vector. Let's go to this URL and complete the code under exercise 1.h. And we'll be back in 4 minutes. Give you 1 more minute. Anyone needs more time? We'll continue. So your program should look something like this. The extract negatives function takes in the vector of integers by reference. It returns a vector of integers. And we have the vector of integers negatives initially as an empty vector, and the for loop starts from the integers.begin iterator. We do the bounce check for it not equal to integers.end. We increment every iteration. And inside, we check if the reference it is less than 0, then we push it back into negatives. So good. Okay. So now let's look at another function that erases all of the negative values in the vector. So in this case, we still take in by reference a vector of integers. And inside here, we go from integers.begin to integer.end. And if the reference of it is less than 0, then it's a negative value. Then we do it equals to integers.erase it. Otherwise, we increment the iterator. So what the integers.erase function does is that it will return an iterator to the next element after the erase happens. So this will erase wherever it is pointing to, and then it will return the iterator to the next element in the vector. And in this case, we're not incrementing in the for loop because erase will point us to the next element. Instead, we increment in the else. So what does erase do? Say we have the vector looking like this. We have the list of processed elements and the list of unprocessed elements we're right here. It points to here, and we see that it's a negative value. Then we call erase it. Then what it does is that it keeps the processed elements the same. It then copies over all of the unprocessed elements to wherever the negative value was. And then it will point the resulting iterator to the next unprocessed element. And this copy is done one by one. So the erase function in the vector class is O(n) time, because we do a one by one deep copy. Then let's count. With this in mind, what is the complexity of the remove negative value of the remove negative function? Can anyone tell me? We know the erase has a complexity of O(n). Yeah. O(n) squared. Yeah, because the remove negatives has an O(n) to go through the loop and O(n) to do the erase. So consider a vector that contains all negative values. The worst case, we'll need to do O(n) squared. In the other hand, let's consider the linked list for erase. The doubly linked list allows for bidirectional access, and it supports a fast insert and erase, because to insert and erase in the middle of a doubly linked list, we just need to update the two neighbors, the next and previous, for the two neighbors. So as a comparison, for the vectors, we have all of these O(1), including random access, and erase and insert given an iterator is O(n) time, because we need to do copies. For list, all of these are O(1). It does not support random access, but erase and insert takes O(1) time, which means that for random access, we can do something like IT plus 5. But for list, we can only do plus plus minus minus. IT plus 5 is not allowed, because it only goes to the next or the previous. Does this make sense? Is this clear? So the design choice of whether to use vector or list is then dependent on what kind of operation you want to do with it. So the iterator categories are then random access, like vector. We can do all of dereferencing plus minus minus plus 5. Bidirectional, like linked list, doubly linked list, we can do dereferencing plus minus minus. Forward only, like a forward linked list, we can do dereferencing and plus, not minus minus. These are just simply not defined for the iterator class. Now, if we consider the remove negatives again, and we replace the STD vector with STD list for a faster erase, we just need to do this. We replace all of the vectors with list, and all the other syntaxes with iterators are the same. Yeah. Erase, you only need to update the two neighbors for the list. But for the vector, you need to copy over everything else after where you are erasing over. So Because of iterators, we can quickly switch from vector to list because the iterators have the same syntax throughout. And if we switch over to list, the remove negatives is now O(n) time instead of O(n) squared. Just be careful that not all code works interchangeably with all containers. Like if you previously had something like IT plus 5, when you switch to list, it's not defined for list. So watch out for that when you are switching between the containers. And something else that is pretty useful is the auto keyword that's introduced in C++11. So the auto keyword allows you to, instead of specifying a type when you are initializing a variable, you can use the auto keyword so that the compiler can determine the type for you. And this saves on typing mainly. And this will keep code compiling when you switch types around frequently. Like if you switch from a vector to a list, and if you are using the auto keyword for the iterator, you don't need to update the iterator code there. But you should always know what the actual type will be. And this is very important when you are using the auto keyword, because the auto keyword can make your code less understandable. And the type is still static. This means that the auto keyword does not change the type dynamically. If the compiler assigns the type when it sees the auto, that type doesn't change. If you do a auto a equals to 2, and the compiler will think that the 2 is an integer. But if you think that when you are assigning the 2, you meant a double, then the compiler will have an error because of this misunderstanding between you and the compiler. So in cases that are very simple, like int or double, just write it. Don't use auto in that case. Now, and for the iterator code, we can simplify it with auto by replacing the std vector int iterator it into auto it. So in this case, the compiler will find what type is number slot begin, and it will replace the auto keyword with this iterator type. Is it clear with auto? Now, even simpler, using iterators, we have the range base for in C++. The range base for is then given any container in STL. In this case, we have the vector numbers. We can do for auto reference item within numbers. And this will default to starting from the begin iterator of numbers. We dereference every element and put it into item. So this item is already dereferenced. And it goes from begin all the way to end. So this is a complex syntax for looping over an entire STL container. This works for all STL containers with iterators defined. Yeah, the auto keyword is a reference so we can change values. It automatically determines the type. Numbers will loop from dot begin to dot end with iterators. And the dereferenced iterator is put into the variable called item here. So this points directly to the object. It's not a pointer or iterator. This is the object itself. And now let's go to the first demo. Yeah, again, just showing you, I have seen a lot of people in the labs who are doing this applications, programming Visual Studio Code something, and then choosing the directory within that. I just want to warn you that the Visual Studio Code here might not be the right version of Visual Studio Code that you should be using. So what you need to do is to go to System Tools, open a Mate terminal, and cd into whichever directory you're in. And in my case, it's this one. Okay. And to open VS Code here, just type code dot. This is the only way you should be doing to open VS Code, if you wish to use VS Code, of course. Any other way could open a VS Code that's not supported or not compatible with something, could have errors. Now, let's look at this code for the demo. So we have the code to do for a large vector. We assign a random number into each element of the vector, and we do remove negatives. This is the code for remove negatives with dot erase. And for the list, it's the same code except vectors replaced by list. Let's look at it side by side. So except for the vector is replaced by a list, all the code are the same. And let me compile the make file. This will compile both programs. And let me so now I want to compare the runtime for both. So let me find the vec erase. Remember that we covered that vec erase does O(n) square. (18.51 seconds. That's the time taken for O(n) square. And let's time the list arrays. 0.09 seconds. That's O(n). So that's the comparison between ON and ON squared. And if we look at the compile flags, we're compiling with -00. That means no compiler optimizations. If we make clean and make configuration equals to release the -03, which is the most compiler optimization you can assign. Now let's do the time again. Still very slow. ON squared. Okay, that doesn't really help, but yeah, you know what I mean. 0.04 seconds for ON. So really avoid any algorithm that is ON squared unless it's absolutely necessary or it's of a smaller number of elements, I guess. Okay. That's the end of tutorial 2A. Now let's go to 2B. Anyone needs a short break? Need a short break? Yeah. We can come back at 4. Okay. Continue with STL containers. Some other containers in the STL. So in tutorial 2B, we're covering associative containers, sequential containers, unordered associative containers, and ordered containers. So why do we use associative containers even if we have something like vector? If we want to find the value in an STD vector, the first option is to do a find. So what STD find function does is that it goes from the beginning iterator to the end iterator that are specified by you, and it search for the actual value inside the vector. So basically brute force. It goes from the beginning to the end and searches for a single value. And this has ON complexity. If we want to find it faster, we can first sort the container and then search with something like binary search. So in that case, you need to first write the code to sort the container, usually with an ON log n time. And then you can search efficiently with O log n time with binary search. So in this case, it's difficult to write. And sorting the container itself is already longer than ON. So only do this if you are searching for a lot of times, but without the need to sort it. But there are data structure that is inherently ordered. Can anyone tell me an example of a data structure that is ordered by itself? It doesn't need to sort. binary search tree from ECE244. Binary search tree. And in the STL, it's called a map. Maps are implemented binary search trees. They are self-balancing so that you don't need to worry about having the worst case of binary search trees being not balanced. So you're guaranteed to have an O log n time to find, insert, and erase any element in the binary search tree. STD map is implemented using pairs, with the first as a key and the second as the value. So you push a pair that's templated to any sort of types into a map. So for example, domain name servers, DNS. If you are going into your browser and you type in a URL, what the browser does is that it contacts the domain name server, and the domain name server will do a domain name lookup to find your domain name as a string and its corresponding IP address as an integer. So the pair stored in the domain name server binary search tree is a pair of string and integer, where the string is the key, value is the integer. An example for inserting into the map, say we define a map where the key is a string, the value is integer, DNS lookup. And then inserting into it, you can either, you have to include the map container to use map. And creating the map that's templated by specifying the key and value. You can either create a pair first using the pairs container, using the pairs constructor by specifying the templated types, key, and value. And then insert Google into DNS lookup. Second option, you can use the STL's helper function to make a pair. In this case, you don't need to specify the templated types. STL will do it for you. And by using the auto keyword, you don't need to specify the types here either. And then you can insert Apple, like this. Option 3, you can skip the auto Apple part and directly insert whatever's returned from make pair. And all of these are for saving on typings, because we are targeting a shorter program. Now, searching in the map. So if we want to look up in the DNS lookup, what should we use to search, the key or the value? Anyone? Tell me. Are you? So remember what DNS does. When you type a URL into the browser sends that URL to the domain name server, and the domain name server will give you the IP address that you should be going to. So what are you searching with? The key. And the key is the string. And we search using the find function that's defined in the map container. So then if we can find apple.com, the returned iterator is not pointing to the DNS lookup.end. And that means that we are able to find it. In the case that Microsoft is not defined here, the return iterator will point to DNS lookup.end. And by comparing that, we can say that we could not find Microsoft. So the find will either return the iterator to the actual element that it's found, or it will return DNS lookup.end if it's not found. And what the iterator is actually pointing to is a pair. So you can use the iterator to access the first and second element of the pair. And we need to dereference the iterator. Now, if we want to iterate over a map using a for loop, let's go back to the exercise URL and complete exercise 2. And we'll be back in 4 minutes. So what we want is use iterators to print out all of the nodes in the map. This could be a little bit counterintuitive because you are outputting everything from a binary search tree, not a 1D array. But you can do it with iterators. Anyone needs more time? I'll continue. Whatever. So to loop through a map with iterators, we do the same thing as before. Auto IT equals to .begin and traverse plus plus until it reaches the end. And then we output the IT dereferenced first and second. Now this should be the output. Notice that the outputted URL are actually sorted compared to what's inserted here. Iterating over a binary search tree is actually an in-order traversal of the binary search tree. And by in-order, it means that it goes from left, center, right. So then whatever is outputted by traversing through the map is inherently sorted. Because left is always less than center, center is always less than right. So what the myMap.begin points to is then the leftmost node of the binary search tree. What the myMap.end points to is one next than the rightmost node of the binary search tree. So the traversal will look like 1, 2, 3, 4, 5, 6, end. And if you want to do find2, it will return the iterator pointing to the actual element. Now consider the case where you have duplicate keys. Say if you have a salary database of strings and float, and you have a person who is named John Smith, and you have another person who has the same name. When you are inserting into the map, the binary search tree, and when you find the John Smith by name, what this will happen is that when it's inserting the second John Smith, the key already exists, so this insertion will fail. So then when you do the find and output, it will only output the first John Smith inserted. What do we do in this case if we need both John Smiths? We go into the C++ reference website, look into the containers library and see if there are any containers that can help. Then we find multi-map. Basically, multi-map is a map that can store multiple keys with the same key, multiple elements with the same key. So for a multi-map, we do the similar things. We still include the map, but in this case, we are defining a multi-map here. Then when we are inserting John Smith for the second time, the second John Smith gets inserted into the multi-map. But then when it finds the John Smith, it will only return one entry because that's what the find function is defined. If you need all of the John Smiths being returned, we go to the documentation again. There should be something that's useful for that. And we find something called equal range. Equal range returns a SCD pair of two iterators that gives a range of entries with the same key John Smith. So we save the range. Remember, when we're using auto, we should at least have an idea of what this should be. We call salary database.equal range John Smith. And this returns a pair of two iterators. So then for the for loop, we start from the first iterator and we stop at the second iterator and traverse by incrementing that iterator. And yeah.
So the first iterator compares to the iterator after the first John Smith. The second one's going to be John Smith.
The second one is one past the last John Smith.
One past the last.
Yeah, it's the same thing like the end. It's always one pass. And this code will output both John Smiths. How this works, the first of the two iterators points to the first John Smith. And because we are in a binary search tree, the same keys are always stored together. So John Smith, and then the next one. Range.second will point to the next after the last John Smith. So we stop when we see range.second. We have other containers, not constrained to all these. We have map, which is the binary search tree that's ordered. Multi-map, that's the binary search tree that can store duplicate keys. We have the unordered map, whereby the name is not ordered. And we have the set. The set is a tree that stores when you only need the keys and not values. So this stores not pairs, it stores single values, single keys. Yeah. Yeah. And you have the other containers. Those are trees. The other containers, 1D containers like queue, when we want first in, first out. We have the priority queue where you can fastly look up the largest or the smallest element. It's the largest by default. So priority queue is sort of the similar sense like the ordered ones. It's just you push with O log n, but pop with O1. So this is good when you only need to have a fast access of the maximum or the minimum element, depending on your usage. We have the stack that does first in, last out, or last in, first out. We have the dequeue that's similar to a vector, but is faster with insertion and deletions. A map versus the unordered map. As you should already see, that find, insert, and erase for unordered map are all O1s. This means that all unordered map is much faster than map because it's unordered. And this is how it's implemented. The map is a binary search tree. The unordered map is a hash table. And that's why it's faster. So binary search trees takes O log n to find an element by key it's inherently ordered, and it can use with any key type that defines an operator less than for comparison. Or you can, if you look at the documentation, you can manually specify another comparator for your map. Unordered map takes O1 to find an element by key. It's not sorted. You can never get it sorted, but you can use the unordered map if your key type has a hash function defined. You can never get an unordered map sorted. So only use it when you don't care about the order. The standard template library is massive. We are not able to cover everything in the STL, and no one can know everything in the STL, but it's very useful. So make sure you know how to search in the STL, and make sure you know how to use whichever container that's useful in the STL. And we have these references online. And we expect you to know how to find whichever container is the best to use in each scenario. And let's go to demo 2. So demo 2 will be a comparison between map versus unordered map. Open it up again for comparison. So we have two files, map search and unordered map search. For the map search, we include the map. We make a map with key and value both integers. We populate the map with some key and value, and we randomly search for 10 times n keys. For unordered map, we include the unordered map, and we use the unordered map, and everything else is the same syntax. And because the syntax are very similar to each other, it's very convenient to try different container types. Now let's do make configuration release. Start from time map search. Remember that map search takes O log n. 0.31. And let's time the unordered map search. 0.17. This is O log n. This is O1. So that's about 2 times, less than 2 times faster with O1. And this depends on the n, size of n. And this means that O log n is good enough. If you want even faster, you have to use O1. Now, that's 2B. Last part 2C. STL algorithms. Apart from containers, STL has another very powerful implementation of algorithms. The algorithms are also templated. We're going to see what kind of algorithms are provided. How can I find a specific value in the container? Remember, we already have seen the find function. How can I sort a container? How can I find the information I need to use the STL on my own? Now, finding the elements. You have a collection of data. You need to find a specific value in the collection, like what we were talking about in the containers. Option 1 is brute force. You write a loop to go through each element and compare. And finish when you have found the element. Option 2, use stdfind. stdfind is the helper function that's implemented in the algorithms header file by the STL. And what it inherently does is that it takes in the iterator to the beginning and end of the container. It will return the iterator to the first match of the value you are searching for. So this does the same thing as option 1. The only difference is that you don't need to write it on your own. And from the call to the function, you know that you are finding something. You don't have to read over a for loop and decide, oh, you're writing the for loop to find something. From the call to the find function, you know from the name that you are finding something. It requires less typing, and we reuse the well-tested code of the find function. So you know that if you get an error, it's not within the find function. But it could be because if you're using a loop, it could be within your loop. So that saves time debugging, and which is a good thing during programming. Finding an element from any sort of container, like list in this case, we can use it equals to stdfind, collection.begin, collection.end, and the value you want to find. Then if it equals to collection.end, that means you didn't find the value. In other cases, you can just directly dereference the iterator and see that you have found the value. In order to use find, you'll need to include the algorithm header. And still auto tells the compiler to determine the type. And now let's go to the third exercise of this tutorial. Say you have a vector of int. Use the stdfind and iterators to write a code that checks that only the first element is 1. So what this needs to check is that first, the first element is 1. Second, except for the first element, no other elements are 1. Let's go to exercise 3. And we'll be back in 6 minutes. The fact that no other ones are not. Okay, I'll continue. I'll tell you the answer. So your code should look something like this. We first check the first element is 1. And we search from first element plus 1 to collection.end for a 1. And this iterator should return collection.end. So if both conditions are satisfied, we say true, otherwise false. So the trick is we need to do a plus 1 here. We have some other functions from the algorithm library, like min, max, sort, that sorts a range, for example, a vector into ascending order by default, or you can specify the compare operator to do descending or anything else. We have the find, we have the swap that swaps 2 values. We have the count that counts the number of elements of a given value, given the start and end iterators, and many, many more. Now let's practice researching in the SDL. Let's find the SCD sort function online and see if you can answer these 4 questions. And I'll wait until you have the web page out. Search for it online. Go to the web page. First question is, how many arguments does the sort function accept? What are the arguments of the simplest sort, of the simplest call to the sort function? How many arguments and what are the arguments? Who has an answer to the first question? Two, three, two. The simplest call to the source function, how many? 2. And what are they? Yeah. Same time, first and last. Same type. What are the requirements on the arguments? They're iterators, and what kind of iterator? Remember, we have 3 types of iterators. We have random access, we have bidirectional, random access iterators. And this is required for the sort function. How are the elements compared by default? They're compared with the operator less than by default. And what is the time complexity for sort? O(n), O(n) log n, n log n. Then using sort, and then print the numbers to std out. It's then just to include algorithm as a header file. Sort given the beginning and end iterators. And they have to be random access iterators because then we're giving in the vector. And then we go from the beginning to the end and dereference the iterator. So that's just an example usage. And after your research, you should know how to call this sort. I know. Okay. Yeah, that's it for today's tutorial. And I'll save here for a bit for any questions. Thank you.